So let's move on to the next method now. So what we've been talking about, I flagged to you guys, was when we had a divisor. I mean, not a divisor, a denominator that was irreducible, which meant it can't be further factorized over the real numbers. But what if you can factorize it? Well, as I pointed out earlier, you'd need to use a technique called partial fractions. So basically what a partial fractions is, when you use it is when the degree of the denominator is higher than the degree of the numerator. So remember, when the degree in the bottom is less than in the top, we can just use long division and simplify the fraction. But when degree in the bottom is higher than the numerator, you have to sort of use partial fractions. And basically what partial fractions is you're breaking down a complicated fraction into the sum of more simpler fractions. So basically, if you wish to find the integral of a polynomial p of x over q of x, where q of x can be factorized into linear polynomials or quadratic polynomials, then there basically exists like sub-polynomials which satisfies this identity, where basically it's a bit complex when you write it like that, but basically it's saying if you've got something like 1 over x minus 2 times x plus 3, there is a way of writing it so that you can simplify this fraction as something a plus something over x plus 3. So something over x minus 2, something over x plus 3. So you can actually simplify it as a sum of simpler fractions, where each new denominator is a factor that you had from the initial denominator, and you just got something in the top. And the rule is, if you have a linear denominator, a linear factor, the top thing will be a constant. It will have a degree 1 less than what you have. But if you had like a quadratic, like for example, something like this, you would have a polynomial 1 degree less. So you would have a linear on the top instead. So you could have, like, if you got like 1 over x squared plus x plus 1 times x plus 3 or something like that, you could have rewritten this as a sum of two simpler fractions. So this is basically the gist of what partial fractions is. You basically split a complicated fraction into a sum of simpler fractions where each denominator of the new fractions is a factor of the original complicated sort of fraction. So let's just begin with a simple case where there's no repeated factors. So there's no like x minus 2 squared or something like that in a denominator. So just basically factorize your denominator. So factorize your q of x into real and linear quadratic factors. So either linear or either quadratic. Then write your expression like that. Then if your denominator is quadratic, put a linear term in the numerator. If your denominator is linear, put a constant. So basically you just want to have the degree 1 less than what the denominator is. Then afterwards you can use either equating coefficients or substituting values, or you can use a combination of both these methods in order to find what the coefficients are. So a bit complicated when I just say it, but it makes more sense when you actually do it. So let's say you want to integrate 1 over x squared minus a squared. Well, we know that this can be factorized as 1 minus, using the difference of two squares. we can factorize this as x minus a, x plus a. So now we can actually use partial fractions to, so I'm going to split this fraction. I'm going to let it be identically equal to, so it's not like a normal equation where it's, remember with x plus 2 equals 7, this will only happen when x is equal to 5. So this is an equation. It's different from saying something like x plus 2 is identically equal to x plus 1 plus 1. Because this will always be true for all values of x. This thing is only true when x is equal to 5. It's only true for a certain value of x. This is an identity where x is always true, no matter which value you put it. So here I'm writing it in a different form. So I'm going to split it as the sum of two fractions, each one with a denominator which is equal to one of these factors of the original denominator. Because they are linear ones, I'm going to have constant numerators. So just like what we did here, I can now combine this into a single fraction. So you know when I write this in a single fraction, I will get this. And because the denominators are the same as each other, I know the top have to be the same as well. So I know that 1 must be identically equal to this thing, which is what's written here on the slides, but this is giving you more context behind how we got that result. So we split it as we let it be equal to this sum of, we let it be equal to the sum of these two fractions. Then we combine it, and then we are going to, we see that because the denominators are the same, we are going to know that 1 is identically equal to a times x plus a, and b is equal to x minus a. So the way you figure out what a and b are is you can either use substitution of smart values, or you can simply you can expand it and then you can compare the coefficients. So let's do comparing coefficients, because I think here we do a substitution, which can be often faster, but I want to show you that you can still do it by comparing coefficients. So this is identically equal to ax plus aa plus bx minus ba. So I can group the like terms together. So this is the same thing as a plus b, x plus aa minus ba. So comparing the coefficients for, so I can compare coefficients. Notice that on the left-hand side, we don't have a term for x, which means that our a plus b must be equal to 0, because the coefficient of x on the left-hand side is 0. There's no x term. So we know that a plus b must be equal to 0. And also, we know that aa minus ba, the constant term, is equal to 1, because the constant term on the left-hand side is equal to 1. So now we can just make a and b the subject. So we can just solve these, we can solve these two equations simultaneously. So for equation 1, I can multiply that by a, so I get aa plus ba is equal to 0. So now I can just add these two equations together. So I can say 2aa is equal to 1, so therefore a must be equal to 1 over 2a. And therefore I can plug this back into equation 1. So I can say that 1 over 2a plus b is equal to 0. So therefore b is equal to negative 1 over 2a. So therefore I can say that, remember, we let this entire fraction inside the integral be equal to this thing. So therefore, we know that the integral of 1 over x squared minus a squared is the same thing as the integral of the coefficient. We said a is 1 over 2a. So this will be 1 over 2a times x minus a. And plus b. B is minus, so it'll be minus 1 over 2a x plus a, like that. So this actually works out. If I factorize out a 2a, it'll be an integral of 1 over x minus a minus 1 over x plus a, which is actually going to be 1 over 2a ln absolute value of x minus a minus ln absolute value of x plus a, like that, plus c, which is yeah, what we got here. So that's how you would integrate 1 over x squared minus a squared. It will simply be this result. And we know how to do this using partial fractions. So kind of a complicated example to start with. I would have preferred doing an example where we didn't have a. Here we would have like an actual number, but here it's just a generalized way it works, even when we have like coefficients and not just numbers like that. Okay. So here so you can see here I did it by comparing coefficients, but another way you could have done it was you could have made smart substitutions. So back in this stage here, you could have let x equals a, so that you get that will cancel out. You get 2a is going to be 1, so therefore a is just 1 over 2a. Then you can substitute x equals negative a to get b is equal to negative 1 over 2a. So that would have been a faster way, but here it shows that both ways are valid. Okay, let's try another example now. So let's say we are asked to integrate 2 over x minus 2 times x squared minus 4x plus 5. So notice how this bottom is already in a factorized form, and also that the top has a degree. The degree of the top is less than the bottom. So the bottom degree is actually bigger than the degree at the top. So we can't use long division. We're going to have to use partial fractions. So just like what we've done here, we're going to let this thing be equal to we're going to rewrite it in a different form. We're going to let it be identically equal to the sum of two fractions, because there's two factors here, where we got x minus 2 because that's one factor, and here we got x squared minus 4x plus 5, which is irreducible. So that can't be further factorized, which is what we want, because if it could be factorized, you would be able to split it into 3 fractions instead, where but in this case it's irreducible, so we could just leave it as a quadratic like that. Notice how this time, because this is a linear factor, the numerator for this fraction is a constant, but for this one, because it's a quadratic, we are left with, we want to put a linear numerator instead. So remember that the degree is 1 less than what it is. So we are going to let it be equal to that. And then basically what happens when you combine it into one fraction is the numerators, when you compare the numerators, you see that 2 is identically equal to a times x squared minus 4x plus 5 plus bx plus c x minus 2. So the way we can do this is you can do what we did last time in order to find what a, b, and c are. You can do what we did last time and expand and compare the coefficients, or you can do substitutions where you can substitute values of x in order to try to get a quick result, or you can do a combination of both. So I think for this question, I'm going to do a combination of both. So I can see easily if I substitute x equals 2, I can eliminate this entire thing quickly. So I'm going to let x equals to 2. So in the left, there's no value for x, so it just stays 2. So 2 is equal to a times 2 squared, which is 4, minus 4 times 2, which is 8, plus 5. And here we get, this is 0, so that entire thing, it goes away. So we know that this is going to be negative 4 plus 5, which is 1. So that is going to be a plus 0 is 2. So therefore, a is just going to be 2, which is lovely. So now we know that 2 is identically equal to 2 x squared minus 4x plus 5 plus bx plus c x minus 2. So now I'm going to expand and then compare coefficients. So this is going to be 2x squared minus 8x plus 10. And here we got bx squared minus 2b plus cx minus 2c. So now we can collect the like terms together. So for x squared, we got 2 plus b x squared. So we got x squared there. For the x's, we got minus 8, which is this one, plus c x, and then we got the constant terms, plus 10 minus 2b minus 2c. So here we can just choose which coefficient we want to compare to. So let's compare the coefficient of x squared. On the left, we don't have an x squared term, so we know that 0 is equal to 2. So we compare coefficients. So 0 is equal to 2 plus b. So therefore, we know that b must be equal to negative 2. And we can also compare the coefficient of x. So we know that 0, because there's no term for x, is going to be minus 8 plus c. So therefore, c is equal to 8. And you can also compare this one with 2, and you can just double check if it's right. So you can see 10 times minus 2 times minus 2. So 10 plus 4 minus 2 times 8. So 10 minus 2 times minus 2 minus 2 times 8 gives you, minus 2. So just double check I did the right thing. So 2x squared. So we know that a is equal to 2. So 2x squared minus 8x plus 10 plus bx squared minus 2b plus cx minus 2c. So our x term. So this is right. We got b is equal to negative 2, but to get c, if x is equal to 0, then 0 minus, so if we had let x equal 0, you could have gotten so if we had let x equals to 0, what we would have gotten is 2 is equal to, we said that a was equal to 2. So 2 times 5 plus 0 plus c times 0 minus 2, which would have been 10 minus 2c. So 2c would have been equal to 8. So therefore c is equal to 4. So what happened here when I was comparing coefficients, bx squared minus 2b. Okay, I think, yeah, I think I realized what happened. This is bx, and that is minus 2bx. So I left out an x here. So be careful. We got a 2bx, so that changes things because this will be minus 8 plus c plus 2b. And here it would have been, instead of a 2b, it would have just been 10 minus 2c. So you could have actually compared the coefficient of this with that. So you would have gotten 2 is equal to 10 minus 2c anyway, so which would give you c equals 4. So yeah, just don't make any silly mistakes like I just did, where when I expanded, instead of saying bx, where this should have been, yeah, minus 2bx instead of just minus 2b. So yeah, c is equal to 4 and b is equal to negative 2 and a is equal to 2. So here I did a combination of comparing coefficients and also substitution. So afterwards, you can then break down this integral into these partial fractions, and then this one you can integrate using ln. This one you can then manipulate to get the reverse chain rule, and then you can integrate it like so. Cool. So, yeah. So let's talk about what happens when we have repeat factors now. So, if you have repeat factors, what you have to do is, if we have ax minus b to the power of m in the factorization, you just basically add a sum of fractions up to that start with like just ax minus b up to that power of m. So basically it's a bit confusing. What I'm saying is, if you have like 1 over x minus 5 to the power of 4, what you're going to have to do is, instead of just having a over x minus 5, you'd do a plus b x minus 5 squared plus c x minus 5 cubed plus d x minus 5 to the power 4. So if you had a situation where you had like in here x minus 1 or something like that, you would let this be identically equal to all of these 4 fractions plus an extra fraction to account for this factor here, like that. So if you had a quadratic repeat factor, it's the same logic, but instead of having a numerator that is a constant, you would have a linear numerator instead. So this is kind of example. We're not gonna actually do it, but this is just to see it in action. So say we had x minus 1 squared. Say we had to actually integrate 125 over x minus 1 squared times x squared plus 2x plus 2, that entire thing squared. What you have to do is, because we have a repeat factor for x minus 1s, we start from x minus 1, sum up all the way to x minus 1 squared. So we've got 2 fractions for that. And here we've got this x squared plus 2x plus 2, the entire thing squared. So we have to start with it and then sum up to it squared. And because of the fact that it's a quadratic denominator, I would have to make sure it's a linear factor instead. Linear numerator. So yeah, then you'd break it down into that, and then you'd have to do some substitution. You'd have to do some manipulation to sort of figure out what A, B, C, D, E, and F are. So yeah, let's not do that. Basically, in the end, if you actually do attempt this, you would get this result. This thing can be broken down as the sum of that, and then you can try integrating it. So let's actually do a question now, like not as complicated as this previous one, but yeah, let's just do this one. So if you got 1 over x squared times x minus 2, here the repeat factor is x, it's squared, so we would go a over x plus b over x squared. So if this was x cubed instead, what you would have done is you would have let this be 1, it would have been a over x plus b over x squared plus c over x cubed, then a d for the x minus 2. But in this case, we have x squared. So we're going to let it be equal to a over x plus b over x squared plus c over x minus 2. Then we can put this all into one fraction, and then we can say that 1 is equal to ax times x minus 2 plus b times x minus 2 plus c x squared. So let's figure out what a, b, and c are. So you can do substitution. So let x is equal to 2. So 1 is equal to 0 plus 0 plus c times 2 squared. So therefore c must be equal to 1/4. And then afterwards you can expand and then compare coefficients. So you get that b is negative half and a is negative 1/4. So then afterwards you can just basically put that back into you could break this thing down into the sum of these partial fractions. And then when you integrate, you'll get this result. Because it's much easier to integrate these individual fractions than it is to integrate this entire big fraction there. So yeah, we are running kind of low on time. So apologies if we couldn't go through the exact comprehensive step-by-step process. Because I do realize that we are running short on time and we still haven't done integration by parts or reduction formulas and that other stuff. So we should make sure we pace ourselves. So just as a side note, with partial fractions, there's actually a shortcut known as the Heaviside cover-up method. We won't discuss it now, but if you're curious, you can check it out in, like, I think it was in the Fitzpatrick or was it in another textbook, but search it up online on Wikipedia. There's like a cover-up factor where it's quicker to find partial fractions. But I don't think you're allowed to use it in the HSC anyway, because if they want you to show your full working.